Collections of attribute groups. Attribute groups can be used when you want to represent a multiplicity in parts of a representation. Issues may have documents attached to them. Those documents would most likely be represented as links. But there may be additional attributes associated with the documents that can be grouped together. This allows multiple groups of these document attributes to be included in a single representation while maintaining the relationship between the document and its related attributes. The following is an example of an attribute group collection. App blows up. Screenshot.jpg. The 3rd of November, 2013, 1015. /document repository /123233. Steps to reproduce.txt. The 3rd of November, 2013, 1022. /document repository /123234. Information model versus media type. So far, we have talked about the information model that surrounds the domain of issue tracking. We have discussed, in abstract, how these pieces of information can be represented, grouped, and related. Figure 5:1. I have avoided the discussion of specific formats like XML and JSON because it is important to understand that the definition of the information model is independent of specific representation syntax. In the next chapter, when we talk about media types, we will address the physical mapping of our conceptual model to the syntax of real media types and their particular formats. Figure 5:1. Information model. There are several things to consider in relation to the reusability of this information model. A. Alt-How-Fit is quite extensive in its listed capabilities. The majority of this information is optional. T. His allows us to use the same model in both the simplest scenarios and the most sophisticated. However, in order to achieve any kind of interoperability, we must draw a line in the sand and give specific names to attributes. F. Fortunately, what we are defining is purely an interface specification. T. Here is no requirement for apply cations to use these same names when they persist data to their data stores, nor is it necessary for them to use those names in the client application's user interface. As long as the semantic meaning of that data is accurately portrayed to the user, all is good. When defining the media types, we must consider what happens when an application wishes to include semantics that our information model currently does not support. Extensibility is an important goal, however, for this application, building interoperable extensibility is out of scope and so will not be part of the information model. That doesn't mean we can't allow media types to define their own extensibility options that will allow specific clients and servers to deal with extended data. Collections of issues. In addition to the representation of an issue, our applications will probably need to be able to represent sets of issues. These are most likely to be representations returned from some kind of query request. In the next chapter, we will discuss the relative merits of building new media types to represent a set of issues versus reusing the list capabilities of existing media types and the variety of hybrid approaches that exist. Resource models. Another major piece of application architecture to consider when building web APIs are the resources exposed. It is not my intent to predefine a set of resources that must exist with an issue tracking API. One of the major differences between an Evolvable API and RPC/SOAP API is that the available Resources are not part of the contract. It is expected that the client will discover resources, and the capabilities of the client will be limited to the resources that it can discover. I do want to discuss the types of resources that an API might expose so that we have some ideas to work with when exploring the types of media types that our client needs to support. It is always good to start with a minimal set of resources. Resources should be quick and easy to create in a system, so as we gain real experience with consumers using the service, we can easily add new resources to meet additional requirements. Root resource. Every evolvable web API needs a root resource. Without it, clients just cannot begin the discovery process. The URL of the root resource is the one URL that cannot change. This resource will mainly contain a set of links to other resources within the application. Some of those links may point to search resources. Search resources. The canonical example of a search resource is an HTML form that has an input box and does a get using the input value as a query string value. Search resources can be significantly more sophisticated than this, and sometimes can be completely replaced by the use of a URI template. Search resources will usually contain a link that returns some kind of collection resource. Collection resources. A collection resource normally returns a representation that contains a list of attribute groups. Often each attribute group will contain a link to a resource that is being represented by the information in the attribute group. An issue tracking application is likely to predefine a large number of collection resources, such as active issues, closed issues, list of users, list of projects. Often a very large number of collection resources can be defined for a web API by using search parameters to produce filtered collections. It is important that when we use the term resource we understand the distinction between the concept and the underlying implementation that generates the representation. If I create an issues controller that allows a client application to search on subsets of issues, the URLs /issues found by =bob and /issues found by =bill are two different resources, even though it is likely that the exact same code generated the two representations. To my knowledge, there is no term in common usage that describes the shared characteristics of a set of resources that represent different instances of the same concept. From this point on, I will use the term resource class to identify this scenario. Item resources. The bulk of the information retrieved via the API will be communicated via item resources. An item resource provides a representation that contains some or all of the information belonging to a single instance of some information model concept. It is likely that we will need to support multiple different levels of details. Considering the example of an issue, some clients may only want the descriptive attributes. Other clients may want all the details that could be edited. There is a wide variety of subsets of information that a client may need for a particular use case. This is one reason why it is important that, for any issue-related media type that we might define, we remain very flexible regarding what information may or may not be included. Just because a representation of an issue resource does not contain the details of the issue history does not mean the information does not exist. This is where the idea of generating resource representations based on domain object serialization falls apart. An object has just one class definition, You cannot pick and choose which parts of the object you wish to serialize based on context with a generic object serializer. When you are determining the appropriate subsets of attributes to include in a resource, it is important to consider several factors. Large representations have the advantage of requiring fewer round trips. However, when only a small amount of data is required, there will be some wasted bandwidth and processing time. Also, large representations have a higher chance of containing attributes with different levels of volatility. Including descriptive attributes in the same resource as current state attributes. We may find that we cannot cache the resource representation for as long as we might like because the current state information changes frequently. Using data volatility as a guide for segregating data into distinct resources can be a very useful technique. The downside to breaking a single concept into multiple resources is that it can make doing atomic updates using a put more difficult. And it introduces more complexity during cache invalidation. Having more, smaller resources means more links and more representations to manage, but it means there is more opportunity for reuse. There is no formulaic approach for determining the best granularity for resources. It is essential to consider the specific use cases and the various factors we have just discussed and choose the most appropriate resource sizes for the situation. Figure 5-2 shows one particular resource model that an issue tracking service might implement. Each of these resource or resource classes will be exposed at a particular URL by the service. W. We have chosen not to show what those URLs will be because they are not relevant to our design, nor should they be relevant to the client. All too often, developers try to do design by URL when building an API. Here are a number of problems with this approach. Designing by URL steers people to try to define their application as a hierarchy or data structure rather than the application workflow / state machine that should be being modeled. Imitations of the chosen implementation framework's ability to parse, process, and route URLs will tend to constrain the system design even further. E-signing by URL also encourages developers to try to create a consistency in their URI structure that is completely unnecessary and potentially constraining to the design. Identifying resources and the relations between them can be completely independent of URI structure, and later on a URI space can be mapped to the resources. This is a unique benefit of systems where clients are hypermedia-driven. When clients construct URIs based on knowledge of the server's URI space, the need for a uniform URI space with a significant structure becomes pressing. Figure 5-2. Resource model. Any client who understands the media types and link relations that we will be discussing in the next chapter will be able to consume this service without any prior knowledge of any of these resources, other than the root. Conclusion. In this chapter, we have considered the conceptual design of our application. We reviewed why we would want to build a system that can evolve and the costs of that choice. We identified the building blocks of our design and reviewed the application domain. Fundamentally, this is a distributed application and will require communication between different systems. To implement this in a manner that will successfully evolve, we need to define the contracts that will be used to convey application semantics between the system components. This will be the focus of the next chapter. Chapter 6: Media Type Selection and Design.